Okay, in this section we'll start talking about building our very first set of library components for the USB to XLR converter. We've already seen in Eagle that we created our very first library right here, and now we'll begin to add parts to it. We're going to use the same basic set of operations for each part that we make, which is we'll create a footprint, then we'll create a schematic symbol, and then we'll create a device or a component, or what I call a part, which is the connection between a schematic symbol and a footprint. As we build each one of these, we're going to rely on the data sheets quite a bit, as well as our own intuition on how it should work. So let's get started. We'll begin by opening up our library that we created last time. And I have a blank library right here. And the part that we're going to use first is the audio compressor preamplifier, which is this SSM2167. This is a part that I really like for audio products because it has great dynamic range. It's also really inexpensive. It's about $2 or so, and it's got a very small package. This Msop package is what we'll begin with, and usually the package's mechanical information, which is what we use to make the footprint with, is at the back. You can see that right now we're going to be working with about a 3mm wide by about a 5mm tall package. And note that our interesting dimensions are going to be the overall package size, not the size of the plastic. So all we've got to do to begin our footprint is use this middle icon, which they call package. And I'm going to call this package Msop-10, which corresponds to the package given by Analog Devices. You can see it also has a JDEC part number. This is kind of nice because a lot of times people will change the designations of things. The manufacturers have their own kind of internal part numbering system. You get TSOPs, but then you get exposed pad TSOPs. You get fine line BGA versus chip scale BGA versus this BGA versus that BGA. But the JDEC standards are universal. They're registered part numbers, and they'll usually have a variant on the end. In this case, MO187, the variant is BA. So let's begin to build our component. So we've called it Msop-10. Create a new package, and you see we're given a very CAD-like package. I'm going to click and give it a description that just says 10-pin Msop JDEC MO187-BA. I believe that was the designation. And then a little bit of a description, 3 by 5mm. Yeah, that's probably all I care about. Okay, great. Now, one of the first things that we're going to want to do is make a basic documentation grade outline. I just want to get a basic outline of this chip. I'm going to put it on a layer, and that's going to come in real handy later on when we build assembly drawings and the like. So what I usually do is I will create a layer, actually it comes built into Eagle, called TDocu, Top Documentation Layer. And I'll use that for assembly drawings. So I'm going to just pick that. That's my personal one. And the nice thing is I'll get, when I go into the CAM process of building the actual manufacturing files, I will get a Gerber file that's dimensionally accurate that shows the placement of each component. So we'll use our wire command because we're just drawing documentation, and we'll do it on our TDocu layer. Because these aren't physical lines, they don't get put down in ink anywhere, they're just lines usually on a paper or a Gerber file. I can set the width to be 0 and have no problem. And I will also set my grid to be in millimeters. And one interesting thing from the mechanical package is to note the pin spacing. I will usually set my grid to be half of this value. And the reason I use half is because oftentimes if you have an even number of pins, you're going to start out plus or minus half the pin spacing. You can see that this is a 0.5 millimeter basic dimension, which means that it has no tolerances. It's a prescribed dimension. And so that's going to set up my grid. All right? So 0.25 millimeters, and I'm going to set my multiple, which tells me where my line spacing is, to be 2. So that will give me lines at every 0.5 millimeters, but I'll be able to snap to 0.25 millimeters. So that's cool. All right, so now we're ready to start wiring. You can do the wiring in a couple of different ways. You could click around and use your X and Y ordinates here to help you out. But I like to use a lot of command line stuff. So even though I'm in the wire command, I just always type wire. Wire. Use parentheses to give you your 2 coordinates. Unlike other CAD systems, there's no commas in between the 2 ordinates of the system. Later on, we'll talk about relative coordinates, but for right now, everything's absolute. So I know from the package outline that this is 3 millimeters wide and 4.9. I'm going to round that to 5 tall. So my basic package outline is half of 3, so negative 1.5 millimeters, and half of 5, negative 2.5 millimeters. And voila, I've got my first corner. Now you notice up here is the bend options, and I've got it set to one of the 90-degree bends. And the nice thing about that is I can just simply put the next, remove the wire command. We're just going to give it another ordinate. If I was to use wire again, it would have started the command over, and I would have lost my existing line. Take my upper right corner. Boom. That's cool. And it's nice and symmetric. And back down to my original position. And I could terminate it with a semicolon. I've just created the basic package outline on the T-docu later. Gotten the overall outline. Now, you know that the package is actually going to be 3 millimeters by 3 millimeters, but the legs stick out that extra 1 millimeter on each side. So that's why I chose this particular thing. All right. Now, the next thing we'll want to do is pin 1 placement. Where is it at? Well, it's down here in the bottom left corner. So I like to use the polygon command because it gives me a nice filled-in rectangle, and it really likes to complain if you have a 0 width thing because it will try to fill it with infinite wide little fill lines. So I'll give it some width this time. I just use my basic 0.127 is the basic width that Eagle uses for silkscreen. So that's a pretty safe one. And I'm going to change the bend radius a little bit, or the corner bend to the rounded corner bend. And you'll see why in just a second. So I can snap in halfway in between things, and you notice it's starting to create bends. Now I make my first one looks good, make my second one not so good anymore. I could go up here and click it that way, but I'm just going to right click with my mouse, which moves it to the next of these guys in the corner. So I just make 4 little corners, and once I've completed it, it makes a nice little dot. Okay, great. Still on T-document. Last thing I want to do is I want to have text. And Eagle has a macro language. All the macros begin with, or attributes, I call them macros or attributes, begin with the greater than symbol. And the one that we want to use is name. I would like to have the name of the part laid down on this drawing as well. Now you notice this is a little bit fat, right? If I get into reference designators like U13, that's 3 digits, even though the 1 is kind of narrower than the U and the 3, but that's still too fat. I could turn it, right-clicking here, I could turn it sideways if I wanted to. That would probably be the easiest way. Or I could just change down the size a little bit. So I'm just going to make it, I don't know, 1 millimeter tall. Will that fit? It gets me 3 digits, and I'm not really envisioning having more than 100 parts in any section, like the U's for reference designators. Maybe on a more complicated design I might have that problem, but for this one I'm good. Okay, so click it there, and I'm done. That's the documentation phase. Remember, this is used to build assembly drawings that people who do pick and place machines will use. So I've got my pin 1 reference and I've got my name, and I've got my basic package outline. That's about all I need. Now let's move on to the silk screen. The silk screen. Silk screen is just a little different in that I want it to be outside the edge. I don't want my ink to be covered up by the chip. So I'm going to use Eagle's standard layer for that, which is called T-Place. Okay? And I'm going to give it a width. This is now going to be silk screen that has to exist on the circuit board, so it needs to have a non-zero width, continuous, good, and everything like that. And I'm just going to make it a little bit on the outside of the chip. I've got my bend radius a little darked up, so let's fix that. Now remember, T-Docu is about building documentation. This is about building ink that's actually going to go on our circuit board. So I, again, would like to have our reference, or our pin 1 reference designator. I'm going to use the same trick. The, come on, polygon. There we go. Make my nice little rounded corners. There it goes. Oops. Let's try this one over again. Got a little out of whack there. I could have typed the word poly as well. That would have worked just fine. So anyway, down here in the lower corner, boom, 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 boom. Now I've got a nice little dot. Different packages, I do different things. Sometimes I'll make a corner like this, where I'll take a polygon and make a filled-in triangle. I've done that with BGA packages a lot. For connectors, I like to actually just put the word 1 for pin 1 in there, something like that. Okay. Last thing, I want to add on the silk screen layers, I want to add the actual name. And we'll do that same way as before, using the text, using the macro or attribute called name. And I'm going to make a couple of changes. First of all, standard Eagle practice is to put those on a layer called T-names. And if you're one of the types who likes to put reference designators, or values for things like resistors, so you have the resistor value right there on the circuit board, that's fine. You would do that on the T-values layer, etc. But I don't typically do that. I'm going to set my my size back to being kind of our standard, which is 0.127. And I also am going to use a bit more of a board house friendly font. It didn't matter for the documentation, but as we start to lay down circuit boards, I want to do things. The word name doesn't really do it much justice, but I really don't want to spend a lot of time trying to render rounded corners. So the vector font has straight corners for everything, which makes the silk screen process a little easier. Now, one thing I've noticed is that some board houses don't like the thinness of the 0.127, which is a good looking size font, but they don't like the thinness of the pen strokes. So this is where the ratio gets changed to 12, which has been one. So you can see that the letters are a little, the strokes are a little fatter. And then we find a spot for it. It doesn't really matter where we put it, because later on when we go and do the actual routing of the circuit board after we've laid down all of our tracks, I will probably do the smash command, which is not on this particular screen right at the moment. But with smash, you can separate out this reference designator text label from the part and move it around. Okay, great. So we're done with text, and now we can start doing the pads. The pads are the SMDs. We'll use the SMD command. This is a surface mount device. If we were doing a connector or a through-hole mount device, they would be called pads, but these are SMD pads. Go figure. Okay, and we'll show you a couple of tricks with that. When we click the SMD command, an SMD shows up for me to place wherever I want. This is the size of the footprint of the pad. So how do we decide that? Well, we go back to the datasheet, and the datasheet will tell us some interesting stuff. Datasheets, mechanical dimensions have different formats and stuff, but this one's pretty standard. You can see that the width of it is at least 0.3, or is at least 0.15 millimeters, and at maximum is 0.30. Now I'm going to stick with 0.30 and have it run right up against the edges of that. So in other words, I'm not going to put any more copper from here to here, I'm just going to keep it right along the edges there. There's not much web that will reflow over the edge when we put the solder down. But this part here, this side view, is kind of interesting. This is sort of some hard-won experience. What happens with solder is you put down a copper pad, and then you put down paste on top of it, and the reflow process will kind of wick it up, sort of like this. Okay? And I want that reflow wicking up to happen mostly here in this direction and not so much over here. If I have too much wicking over here, I lose the ability to, I lose my clearance over between two pads, and I don't want that. But in this direction, I got all sorts of space. I got parts underneath and anything that goes off the edge. So mechanically, I want my strength to come from the toe and the heel of this kind of foot. And actually, the best mechanical strength actually comes from the heel. So I'm going to make my widths be a little bit bigger than 0.70, which is the maximum, but not too much. I'll probably make it 0.75. Maybe I'll stick with 0.70. We'll just kind of see how it looks. But I want it to definitely be bigger than 0.5, the nominal value, and I don't want to go any bigger than this. So my values that I'm going to choose are going to be 0.75 millimeters tall and 0.3 millimeters wide. So in order to do that, I just go up here into the SMD section, and I say 0.3, an X character, and 0.75, width by height. And now I have this nice long, thin little guy. Now remember, I set up this red outline to be our nominal maximum dimensions. Okay, so this is good because this tells me that this red area is where the toe and the toe are going to be. So since I made my 0.75 just a little bit bigger, I've got a little hanging down below that red horizontal line. That's good. That's what I want. It's not very much, and we could do the math and everything like that, but I'm not too terribly worried about that. So I like where this is looking right now. I've got plenty of heel meat for it to wick up, and I don't have any extra width from between the two pads. So let's start by giving it a name. I'm using the keyboard again, and I want to call this pin 1 because I'm going to start at pin 1. In order to name an SMD pad, it's a text label, so I'm going to use an apostrophe or a tick with the letter 1, the number 1. And Eagle will automatically increment. Now it automatically started with 1, but maybe I had something like I wanted to call them A and B and C and D or something like that, or ground 1, ground 2, something. It will, once you've picked your first one, the next pad will have the next, it'll just keep adding. So if you started calling it, the first one called it ground, the next pad would be called ground 1, ground 2, etc. So it'll try to tack a number on the end. If you started with ground 1, it would go to ground 2, and so on. So, number 1, and I have an odd number of pins. I have 5, so this is the middle one, 3, 2, and 1. Here's pin 1. Pin 1, pin 2, pin 3, 4, and 5. I'm not going to do the top row because I'm going to do something just a little different with that. You noticed when I hit SMD, it changed my layer to top, so don't get confused by the red on red coloring scheme. Top, remember, is a layer of actual copper, and T.U is a contrived layer that we will use later on in CAM to create different things. If you've worked in AutoCAD, for example, you'll know that layers are a very handy way of organizing your information and stuff. So I don't have much choice. I can only go to either top or bottom with these particular ones. Don't worry about roundness. We'll work with that when we want to make round pads, but for the most part, I'm good with everything. Okay. And the angle, unfortunately, this version of the Eagle only has 90-degree rotations, right? So I can only, this is what a 270 looks like, for example. Okay, so I'm done with the bottom row, and now we're going to do something that I like to do quite often, which is to cheat. I'm going to ignore my T.U for just a second, and these are just my pads. Okay, what I'm going to do is I'm going to, rather than creating 5 new pads up on the top and worry about flipping them and making sure everything's right, I'm going to copy this as a group. So I selected my group command here, And grouping is not the same. Copy and paste is not exactly the same in Eagle as you're probably used to with Windows. But I've just selected them just by dragging across them. They're highlighted a little bit. And now I'm going to copy them, relying on Eagle's inherent ability to renumber things as we see fit. I start from the origin, okay, and I right-click, and it pops a context dialog box that says Copy Group. Yes, I would like to copy that group. Now you notice right now I'm on top of them. I can slide a little left, but here's the magic. I'm right-clicking, and right-clicking rotates the group. I'm staying at the origin, which means that it's now rotationally symmetric about the origin. This is really handy for quad flat pack packages that have 4 corners, and you don't want to keep flipping them around or something like that. This is a handy trick. It's not so useful on this one, but it is a good, simple example. We probably didn't save very much time. Click once, and there we go. Now, the all-important quality assurance phase, right? What is the pad? Did I give it the correct pad numbers? Let's check. Using the eyeball or show command, I can look at each one, click on it, and you see down in the corner it will tell you its name. SMD 1, 2, 3, 4, 5. You notice that the pin out of this package is rotationally oriented counterclockwise. So I want to make sure that that happens. So this one should be 6, which it is. 7, 8, 9, 10. The new versions of Eagle have a feature up in the options menu to turn on viewing of the pin numbers. This version did not have that, so I wrote a little program. So, which I'll post to anybody who wants to do it. And this is a user language program. I make lots of these. And this one's called Document Package. And what it does is it drops everything onto the layer called pin names. Don't worry about size or anything, etc., etc. And it's basically creating a sequence of text commands that will put text on a layer that I can see. So I could have typed all these things in, but I'll do a separate segment on user language programs. Anyway, the point is there's now a layer called pin names. Turn on my documentation again. And I can see right there, yep, these are the pin names, and they look right. This quality assurance is really important. So congratulations to us. We have just completed our very first part. We will do many, many more of these later on. But we've checked to make sure the dimensions are correct. If you ever have a strange measurement question, you can use the info button. And let's say I want to see if this is long enough. It tells me the length. It's 5 millimeters, which is good. That's what I want. 4.95. Good deal. I'm very happy with this part. So that's that completes it. We'll save our file, and the next thing we will do is begin making the schematic symbol for it.